Scene script. Have you ever wondered how fire burns or why rust forms on iron? What if I told you that both of these phenomena have a common chemical process at their core? Enter the fascinating world of oxidation and reduction reactions, or as they are more commonly known, redox reactions. These are the unassuming heroes of chemistry, silently orchestrating a vast array of natural and industrial processes right under our noses. Let's start simple. Oxidation is a process that involves the loss of electrons, while reduction is just the opposite, the gain of electrons. But there's a twist. These reactions never occur alone. They always happen in pairs, forming the inseparable duo of a redox reaction. Think of it as a dance of electrons. In this dance, one molecule struts forward, shedding its electrons and becoming oxidized. Meanwhile, its partner gracefully accepts these electrons, becoming reduced. Now you might be thinking, that's all well and good, but why should I care? Well, the answer lies all around you. Every time a log crackles in a fireplace, oxidation is turning the wood into heat and light. When iron rusts, it's actually being oxidized by the oxygen in the air. And it's not just about burning and rusting. Redox reactions are integral to countless industrial processes. They help us extract metals from their ores, create batteries, and even produce the chlorine that keeps our swimming pools clean. But that's not all. On a more fundamental level, redox reactions are the lifeblood of our very existence. They power the cells in our bodies, allowing us to breathe, move, and think. As we peel back the layers of complexity, we find that oxidation and reduction reactions are more than just chemical jargon. They are the very essence of many processes that we see and experience in our daily lives. So, the next time you see a fire burn or rust forming on iron, remember the silent dance of electrons that makes it all possible. Now that we've understood the basics of redox reactions, how about we dive deeper and explore the fascinating world of titration half reactions? So, what exactly are titration half reactions? Well, they're essentially a way to break down complex redox reactions into simpler parts. Just as a building is constructed from individual bricks, a redox reaction is composed of two half reactions, one for oxidation and one for reduction. These half reactions let us see the step-by-step transformation of reactants into products, which can be a real game changer when trying to understand intricate chemical processes. Let's take a closer look. The titrant, or the solution of known concentration, reacts with the analyte, or the solution of unknown concentration. In a redox titration, the titrant is an oxidizing or reducing agent, and the analyte is a reducing or oxidizing agent. We can view this process as two separate half reactions, the titrant undergoing reduction and the analyte undergoing oxidation, or vice versa. Take the reaction between potassium permanganate and iron 2, for example. The permanganate ion acts as the oxidizing agent, undergoing reduction in the process, while the iron 2 ion acts as the reducing agent, undergoing oxidation. When we write out the half reactions for this process, we can see exactly how each reactant transforms into its respective product, giving us a clear picture of the overall reaction. But that's not all. Titration half reactions also play a crucial role in balancing redox reactions. By balancing each half reaction separately, we can ensure that the total number of electrons lost in the oxidation half reaction equals the total number of electrons gained in the reduction half reaction. This is the key to maintaining charge conservation in a redox reaction. Titration half reactions serve as the building blocks of our understanding of redox reactions. They provide a detailed picture of the chemical transformation taking place. So next time you're faced with a daunting redox reaction, remember to break it down into its half reactions. It's like solving a puzzle. Piece by piece, everything starts to fall into place. Ready to plunge deeper into the world of redox reactions? Ever heard of the Nernst equation or redox equivalent weights? Let's dive in, shall we? First up, the Nernst equation. This is a mathematical relationship used to calculate the potential of an electrochemical cell, or put simply, the voltage of a redox reaction. It essentially tells us the equilibrium between the oxidized and reduced forms of a species in a redox reaction. The equation is named after the German scientist Walter Nernst, who first derived it in the late 19th century. The Nernst equation takes into account the standard reduction potential, temperature, number of electrons transferred, and the concentrations of the oxidized and reduced species. By manipulating these variables, we can predict the direction and extent of a redox reaction. Isn't that fascinating? Now, let's turn our attention to redox equivalent weights. The equivalent weight of a substance in a redox reaction is the mass of that substance that gains or loses 1 mole of electrons. It's a handy concept that helps us determine the amount of a substance that is reduced or oxidized. Consider a simple reaction where iron, C2, is oxidized to iron, 3, by an oxidizing agent. The equivalent weight of iron in this reaction would be its molar mass divided by the number of moles of electrons lost per atom of iron. These two concepts, the Nernst equation and redox equivalent weights, are like secret weapons in the world of redox chemistry. They provide us with the ability to predict and quantify redox reactions, making them less mysterious and more manageable. By understanding these tools and how to use them, we can navigate the complexities of redox reactions with greater ease and precision. The Nernst equation and redox equivalent weights are powerful tools at our disposal. They empower us to predict and quantify redox reactions. So are you ready to put them to use? Moving forward, let's explore the colorful world of redox indicators and the different types of titration. Redox indicators, like their acid-base counterparts, play an essential role in titration, which is a process to determine the concentration of an unknown solution. They signify the endpoint of a titration by changing color. In redox titrations, these indicators respond to the potential of the system rather than the pH. Now let's dive into the fascinating world of various types of titration. Starting with potassium permanganate titration, it's known for its self-indicating ability. The purple permanganate ion reduces to the colorless manganese ion, signaling the completion of the reaction. Next up is keriometry, a versatile titration method using cerium perfoy as the oxidizing agent. Cerium 4's potential to oxidize a wide range of organic and inorganic substances makes it a popular choice in redox titrations. Then we have potassium dichromate titration, a classic example of redox titration. Potassium dichromate, with its bright orange color, reduces to a green chromium ion, providing a clear visual endpoint. Iodine titration follows a similar principle. Iodine, with its characteristic blue-black color with starch, vanishes at the endpoint when all iodine has reacted. Periodic acid titration is a bit different. Here, periodic acid oxidizes certain functional groups in organic compounds, and the endpoint is detected by a visual or potentiometric method. Potassium bromate titration, sodium nitrite titration, and titanious chloride titration all work on similar principles of redox reactions, each bringing unique properties to the table, making them suitable for different types of analyses. From indicators changing colors to different types of titration, the world of redox reactions is truly a spectacle to behold. As we come to the end of our exploration, it's time to take a step back and appreciate the big picture. We've journeyed through the fascinating world of oxidation-reduction reactions, unraveling their mysteries and observing their profound influence on our daily lives. We started by defining these reactions, where we saw how the transfer of electrons from one element to another leads to a change in oxidation states. This simple yet powerful process is the driving force behind many natural phenomena and industrial processes. Then, we delve deeper into the heart of these reactions, exploring the Nernst equation. This mathematical marvel allows us to predict the potential of a redox reaction under non-standard conditions, proving invaluable in fields ranging from electrochemistry to environmental science. We also discussed the concept of redox equivalent weights. As we discovered, understanding this concept is crucial for quantifying the amount of substance that has been reduced or oxidized in a reaction. This knowledge is particularly useful in laboratory settings, where precise measurements can make or break an experiment. From there, we moved on to redox indicators and various types of titration. We learned how these tools help us determine the endpoint of a titration process, which is vital in a multitude of scientific and industrial applications. We examined titrations with potassium permanganate, cereometry, potassium dichromate, iodine, periodic acid, potassium bromate, sodium nitrite, and titanious chloride, each with its own unique applications and challenges. But our journey doesn't end here. The world of redox reactions is vast and ever-evolving, with new discoveries and applications constantly pushing the boundaries of what we know. As we continue to explore this fascinating subject, we'll gain a deeper appreciation for the intricate dance of electrons that fuels our universe. So, the next time you see a fire burning or rust forming, remember the intricate world of redox reactions that's at play. Subscribe for more because you won't find me later.